Problem 114. Here we have these two links, a crank and also AB link. And we are releasing everything from rest from this condition. We know the mass and also mass moment of inertia of this crank about point O. Also, we know the mass of AB. So based on, due to gravity, it's gonna fall down and go to this condition. Let's say this is point O, and this is link AB. And the question is, when OA become vertical, what is the velocity of B? What is this velocity? That's what we are looking for in this problem. So we have two conditions, 1 and 2. And again, we should use work energy equation between these two conditions to find the velocity, right? So before doing that, let's talk about this condition a little bit more. So at this condition, OA is going to rotate. Let's say the angular velocity of it is going to be omega. And velocity of A is going to be OA times omega. And it's going to be perpendicular to this link, which means it's going to be horizontal. So the velocity here is going to be 0.4 times omega of that link, velocity of A. Now look at AB, this link AB. Velocity of A is in the horizontal direction, and velocity of B is in the horizontal direction too. We can show velocity of these 2 points must be equal. There are different ways to show it. For example, if you remember, I said if you choose 2 points on a rigid body, velocity of them times cosine of the angle between the velocity and connecting line must be equal for these 2 points. A and B, both of them are on the same rigid body. So velocity of A times cosine of this angle must be equal to velocity of B times cosine of this angle. But at this moment, because velocity of A and B, both of them are in the horizontal direction, these two angles, they are equal. So because of that, velocity of B must be equal to velocity of A as well. So if velocity of B is V, velocity of A is gonna be V as well. That's important to know, because when we are writing the kinetic energy of this link, then it's gonna be equal to mass, 1/2 of mass times velocity squared of the centroid of it, plus 1/2 of I times omega squared. But because the velocity of 2 points on a rigid body, they are exactly the same in the same direction, omega is equal to 0. So omega of AB at this moment is equal to 0. And also, because omega is equal to 0, velocity of all the points on that rigid body would be the same. For example, velocity of the centroid is going to be V as well. Velocity of B, velocity of A, velocity of the centroid, all of them, they must be the same. That's an important point. Now, going to work energy equation, T1 plus V1 plus U prime from 1 to 2 is equal to T2 plus V2. T1 is 0. T2 T2 is gonna be equal to V2. If I put my reference line here, then potential energy of the crank is going to be 0, and potential energy of the bar is going to be mass of the bar times 0.4, negative. So negative m of the bar times g times 0.4 meter. U prime from 1 to 2 is 0. We don't have any unconservative force that doing work. It's going to be equal to, we have two bodies, we need to calculate the kinetic energy of them separately and add them together. kinetic energy for the bar OA, for this crank OA, is going to be 1/2 of IO times omega squared of it, omega of the bar. But what is this omega? I can write it in terms of velocity of B, or velocity of every point on this bar. Omega is going to be equal to velocity of A divided by OA. So it is equal to V divided by 0.4. So 1/2 of IO times velocity of AB divided by 0.4 squared. And we know what is IO. The question says the radius of gyration for the radius of gyration of OA about 0.0 is given. So IO is gonna be the mass of this guy, which is 12 kilogram times radius of gyration is squared, and the radius of gyration is 0.22. So from there we can put it here. And the energy of AB is going to be 1/2 of its mass, m of the bar, times velocity squared, plus 1/2 of IG omega squared, but omega is equal to 0 here, plus potential energy. Potential energy of both of them are going to be negative. For the crank OA, it's going to be negative m of OA times G times 0.18. That's going to be the height of the centroid. It's given here. And for this bar, it's going to be 0.4 plus the distance from here to here is 0.8. From here to here is 0.4. So from here to here is going to be 0.4 as well. So half of it from here to here is going to be 0.2. So the height for the centroid of this bar from the reference line is going to be 0.4 plus 0.2. So it's going to be 0.6 negative. So minus m of the bar, I should have write it MAB, times G times 0.6. Now if you look at this equation, the only unknown here is V. So we can find V from here. After putting the numbers, V is going to be equal to 2.29 meter per second.